Welcome to Study Loop.
In this problem, you are asked to determine the distance between these two lenses if you are given the focal lengths for both of these lenses and you know the original object distance from the first lens and the image distance for the second lens. So we're going to do that in two parts. So we want to know what this distance is. We're going to first solve for the object distance for the second lens. So we're going to solve for DO2. Now, because all of my numbers, or most of my numbers, are in centimeters, I do want to just leave it in centimeters and actually convert this DO1 to centimeters when I need it. So I'm going to use the thin lens equation. So that's 1 over DO plus 1 over DI equals 1 over F. And we want to solve for DO, so that's 1 over DO equals 1 over F minus 1 over DI. And then solving for DO by inverting the left side and then inverting everything on the right side. Again, because this is talking about the second lens, I'm going to go back and add little 2's to all of this. And then this is 1 over 0.6 minus 1 over the image distance for the second object, for the second lens, which is negative 100. It does tell you that it is to the left of the second lens. So if it tells you it's to the left of the second lens, and that's only true for images, but if it's to the left of the lens, it is negative. If it's to the right of the lens, it's positive. Again, that is only for the images. Again, plugging all of that into your calculator, you should get a distance of the object of 0.596 or 0.6 if you round up. What that tells you is that my image of the first lens is located a distance of 0.6 centimeters from the second lens. So here, this point is DI2 and DO2. Ooh, correction. That's DI1. DI1 equals DO2. Okay, so now we know what the image distance is. That's not true. Just DO2. But now that we know that it's 0.6 centimeters from the second lens, we want to know what this distance is. Okay? And this distance is actually going to be DI1. And we can calculate that distance using, again, the same equation. So instead of solving for DO, I'm going to solve for DI. So 1 over DI equals 1 over F minus 1 over DO. DI equals 1 over F minus 1 over DO. Again, all of these are 1's. And then I get a distance of 3 centimeters here. Okay. That tells you that if DI1 is 3 centimeters and DO2 is 0.6 centimeters, then the total distance between these two lenses must be 3.6 centimeters. Again, that's distance between these two lenses. Okay, so for the next part, for angular magnification, we actually need to know what my linear magnification is before we can solve for this. So we are going to write down some of our values. We said, again, this is DI1, and then this here was DO2. And then we're going to make some room by clearing some of this out. So again, for this next part, we're going to solve for linear magnification first. That's going to help us solve for our angular magnification a little bit later. Okay. So to solve for my linear magnification, this is di1 times di2 all over do1 times do2. So di1 was 3 centimeters. di2 was negative 100. do1 was 20 times 10 to the 2. And do2 we solved to be 0.6 centimeters. And this gets you a magnification of 0.25 negative. So my height of my image is negative 0.25 times my height of my object. Now I don't know what my heights are, but I'm going to use this relationship in my angular magnification equation, which is height of the image times do1 divided by di2 times the height of the object again. So for hi, instead of using hi, I'm just going to put negative 0.25 ho. And the reason that's helping us, so this is 20 times 10 to the 2, is because these HOs are eventually going to cancel out. And I get an angular magnification of 5.